Okay, is it time to start?
Okay, good afternoon, everybody. The first speaker of the afternoon session is Professor Jean-Pierre Desmailly. The title is L2 Extension of Theorems and Applications to Algebraic Geometry, second part.
Okay, thank you very much. So, well, I'm going to continue lecturing on extension theorems, and today I will concentrate on extension with effective estimates and optimal ones. The talk will be, of course, related to what I explained yesterday, but largely independent. Okay, so I recall the setup. So you take a holomorphic line bundle L over a scalar manifold X, and you assume that L is equipped with a singular Hermitian metric, which you write as a smooth one, H0, multiplied by a quasi-plurisobharmonic weight factor, exponential -5. And then you take an extra weight, psi, which is supposed to be locally integrable, such that the sum of the two, phi plus psi, is also quasi-plurisobharmonic. As I explained yesterday, essentially the singularities of psi will define a subvariety Y by looking at the conductor ideal of I of H exponential minus psi divided by I of H. So this is essentially a subvariety where the two ideals differ, and this one has more zeros along the singularities of psi than I of H. Okay, and now you take a section F in the quotient of the ideals, so the I of H divided by the smaller one, with values in Kx tensor L, where Kx is the canonical bundle, and you want to extend it, which means actually lifting as a global section on X of the ideal sheaf I of H. So here, H can be singular with arbitrary singularities. It can also be non-singular, in which case, if it's non-singular, I of H is simply the trivial sheaf. Okay, and this one, the quotient sheaf is supported on subvariety Y. Okay, and now you have the quotient map here, and you want an extension, which means a lifting by going to the quotient. And moreover, and that's the difference with yesterday, we want an L2 estimate for capital F on X in terms of an L2 estimate for small f on the subvariety Y. Okay, of course, we need some convexity assumption, and we assume here that X is weakly pseudo-convex. So, for instance, it can be compact Keller is enough, or Stein, or can be a, for instance, can be holomorphically convex, so it can be proper over a Stein base. That also works. In any case, we assume given a smooth plurisobharmonic exhaustion gamma on X. So if X is compact, simply take gamma to be 0. We need to explain what will be our L2 estimates on Y. And for this, Takeo Ozawa has introduced what I call the Ozawa residual measure. And that would be a measure supported in Y, and it's intrinsically related to the data. Okay, so what is this, this measure? So you start with the section F, okay? So F is given. And now you take a Stein covering, ui. And then, of course, on these Stein open sets, you have liftings because the cohomology vanishes. So you have liftings f twiddle I on ui with coefficients in the multiple ideal sheaf I of h, okay, via the quotient map. But of course, it's only local. So if you want a smooth, if you want a global one, a priori, you can do this by a partition of unity, and then you glue the local liftings by the partition of unity. So you write f twiddle equals sum of xi fi twiddle. And then it turns out that you can define intrinsically a measure as follows. So take a continuous function with compact support, g on y, and then you extend it to x just topologically. It's just a continuous extension with non-negative functions, g twiddle, that extend your given function g on y. And now you want to define your measure. So this is the measure here. It depends on y, of course. It depends on f, or rather the square of f. It depends on the metric h. It depends on the weight psi. Okay, so you want to define what is the integral of a continuous function g. Then you take the infimum over all possible extensions g twiddle of some limb soup of integrals of the extension on tubular neighborhood. So let me draw a picture. So you have here your subvariety y. Now you consider these sets here, which are just tubular neighborhoods. Okay, so there are things like this. Okay. This is a set where psi of z is between t and t plus 1. So here you are near the singularities of psi, so y is contained in the singularity set of psi, so the minus infinity points. So now you take t very negative, so t goes to minus infinity, okay? And when t goes to minus infinity, of course, you get tubular neighborhood, but with a hole. Okay, there are some sort of annuli along y, and you integrate on these annuli here. Okay, so you integrate on this part here along y with respect to the exponential minus psi. Of course, exponential minus psi goes to plus infinity, and at the same time, the volume goes to 0. So you have a compensation, and you hope that the compensation of this term going to plus infinity and the volume going to 0, plus eventually the fact that the function f may vanish, okay, and that you will have an exact compensation of the vanishing of f, the explosion of exponential minus psi, and the decay of the volume, so that you get a convergent integral. So this is exactly the definition. And the observation is that if you get something, well, it's a limb soup, so it's always defined. It can be 0, it can be plus infinity, of course. But whatever it is independent of the choice of the extension f twiddle here. The reason is that if you change to another one, so you get a difference, I denote by delta fi twiddle, so it's the difference of 2, but since they are both liftings, their difference is in the ideal of h exponential minus psi, but then it means that the difference precisely is globally integrable with respect to this weight. And since it's globally integrable with respect to this weight, and then you integrate on something that shrinks to empty set, of course, by the Fatou theorem, this is going to converge to 0. G twiddle, of course, is bounded because compactly supported. So you easily see that you get something absolutely independent of the extension. So although you define it with the extensions, in the end, it depends only on F. Okay, so let me give examples. So the easiest example is when psi is given by a section of a vector bundle. So essentially, you want Y to be the 0 set. Okay, you want Y to be the 0 set of some section. And you assume that you have a rank R bundle. And then you take exactly R times the logarithm of the square of the norm of the section. Assume for simplicity that the metric HE here is smooth. I don't necessarily assume the section to be transverse to 0, but I assume that it is generically transverse to 0. So there might be some singularities, but at the generic point, S defines a transverse subvariety. And of course, I may have singularities where the determinant is 0. So I take the Zariski open set where the determinant is non-zero. And then the precise formula for the Ozawa residue measure here is some universal constant depending only on dimensions times the square of the norm of F with respect to our matrix times the volume form on Y. So the area of Y may have singularities, of course, but I'm here at a regular point. Yeah?
There is a question.
There is a question. So let me look at the question. So more chat. Well, the question is why I put F square. Well, it's just to indicate that it depends quadratically on F and not linearly on F. I could just write F, of course. It has no significance except to mean that it depends quadratically on F, or the square tensor product of F by itself. It doesn't have a precise meaning rather than that, okay? And here I have to divide at the denominator by the Jacobian of the differential of S. So especially it will explode at points where I have singularities. So this measure here need not be locally finite at the singular points, at least if F is non-zero there. Of course, if F vanishes at the singular points, the zeros of F may compensate for the fact that the Jacobian here degenerates, okay? And that might be a requirement to get convergent integrals. The proof, of course, is extremely simple. You simply take normal coordinates, so you pick a holomorphic frame that is H orthonormal, HE orthonormal should have written, and coordinates that are orthonormal at the given point with respect to the Kähler metric. And then you can always diagonalize at the point nearby by writing S of Z as given by the components lambda J, Zj with some eigenvalues. And then you compute, and it's just computing areas of ellipsoids. So I leave that as an exercise. And of course, the volume of the ellipsoid enters into the game, and this is why you have a Jacobian. A slightly more involved case is the case of normal crossing singularities. So here I take psi to be a quasi-pluriharmonic function, which is a sum of some constants Cj positive times the sections vanishing along a non-singular divisor dj, so that I have a simple normal crossing divisor, d equals sum of cj dj, real divisor with positive coefficients. And here I take any smooth metric on the corresponding line bundle OX of dj. This produces a quasi-pleurisomanic function, and I can try to evaluate the Ozawa measure. Okay, so my function I can reduce in coordinates. So because I assume normal crossing, so I can assume my sections are just coordinates. And then I have an extra smooth term. But it's easy to see that if you had a smooth term, because you have exponential minus psi, it just multiplies the measure by the bounded term exponential minus u. So actually, you don't have to care about this. You can ignore this up to somehow a function that is well understood. Okay, now you apply the Fubini's theorem. And if you are at a regular point, so namely on one of the components minus the others, and say d1, so suppose you're on d1, then you have to integrate something like this. So you have the exponential minus psi, which gives you modulus of z1 to the power 2c1. And now you integrate this on annuli, which are defined by exponential t less than z1 to the 2c1 less than exponential t plus 1 by definition. And this you will see very easily that if c1 is an integer, you may have a chance to get something non-zero, provided, so assume c1 is an integer m1, and assume that your function f, you have to remember that it's an ideal sheaf with nilpotent elements. Okay, so it may be zero on z1 equals 0, but you are looking at the nilpotent structure, so you look at the higher order terms. Okay, so you may have a germ which is 0 with multiplicity m1, but does not vanish at order m1 minus 1. So you can simplify in that case by z1 m1 minus 1 times a non-zero factor h twiddle of z. And in that case, it's very easy to see that if you have exactly z1 square left, it will converge to this non-zero value. Okay, the special case, of course, is m1 is 1. Then you don't need the function to vanish. It will converge to a finite non-zero limit. But if it's an integer that is strictly larger than 1, you need some vanishing of f to get something finite. On the other hand, if c1 is not an integer, you can only get 0 or infinity. So it doesn't converge to anything interesting somehow. So the only interesting case is when you happen to have integral multiplicities in this normal crossing divisor. Okay, this is just what I said. Okay, and now let us slightly generalize this by taking a function psi. So psi is what defines my subvariety y. Somehow it's some sort of equation of y, which is given by general analytic singularity. So it means that I have locally psi equal to a constant times log of a sum of squares of holomorphic functions modulo smooth term. And then it's interesting to look at the multiple ideal sheaf of exponential minus s psi. So not just minus psi, but you may take a multiple. So you might want to increase the multiplicities. So you take a multiple. And And then, of course, you can assume C equal 1 because it will be absorbed by S. Then by Hironaka, it's well known that you can blow up the ideal by a composition of blowups, which I know by mu. So it's a modification, x twiddle to x, so that the pullback of the ideal now is an invertible ideal sheaf given by a normal crossing divisor. So you are going to reduce yourself to the previous case. And then there is a simple direct image formula that computes the multiple ideal sheaf. So you go upstairs, okay, but then you have a Jacobian, of course, because the blow up is not to account this vanishing, which means that you plug the relative canonical sheaf of x twiddle over x. And then you compute the direct image of the ideal sheaf upstairs. Actually, this relative canonical sheaf will be given by some of the components with certain multiplicities depending on the number of blowups. And then it turns out that you have to compute the direct image of, so you multiply by S, so you have SMJ dj, but then you have integral parts because, of course, convergence takes the integral parts, plus the coefficients AJ. Okay, so now you have up to Hironaka, of course, which is a not very explicit theorem, you can compute explicitly the multiple ideal sheaf as a direct image of a line bundle given by a normal crossing divisor. And it will be interesting to observe that then you have a discrete sequence of rational numbers for which you get jumps here. And these jumps start at 0. Of course, for 0, you get the, well, some sheaf, which is a trivial sheaf. Of course, the corresponding divisors are exceptional, so you don't get, for s equals 0, you get OX. And then you get a sequence of rational numbers for which these products, SMJ here, take integer values, okay? Not all of them necessarily, but okay. And the measure will be interesting precisely when you compute for these jumps and you take a function that vanishes just at the previous order, because this is exactly when you are expected to get something finite and non-zero. Okay, and now one introduces what I call restricted multiple ideals. So by definition, I introduce an ideal which I denote by I prime psi of h, which is contained in I of h. It's the ideal of germs, actually restrictions of germs, for which the measure is locally finite. We have seen that we have a condition that f actually must vanish somewhere. And this is exactly the condition that defines this new ideal I prime psi of h. By definition, it is contained I of h, and also it contains only h of exponential minus psi. The reason is that, of course, if you are globally integrable on x, then of course by restricting to the tubular neighborhood, you are still integrable. So you have a limit that is possibly 0, but anyway finite. Okay. And the typical case of application is precisely when I have I consider a jump. So of course by rescaling, you can assume that the jump is equal to 1. So assume that some jump sk is 1. It might be the first jump. So the first jump means that this is actually, if you have the first jump, it means that this is OX for S less than 1. And then you suddenly get a non-trivial ideal for 1. So it means that you have log canonical singularities by definition. And that will be especially interesting. And then you can easily see, in general, that this restricted ideal is contained in the ideal corresponding to the previous jump. But there may be some additional constraints on a certain subvariety Y that depend on the singularity. So it's rather complicated. Of course, can be computed by Hironaka, but it's a very subtle thing. Anyway, all this is completely intrinsically defined. Okay, and now I'm almost ready to state the general theorem, except that I want optimal constants according to Joe and Zhu. And here, well, I have introduced something that is slightly differs from their notation, but it's completely equivalent. So you want to consider some flexible weights in the form of some strictly decreasing functions. So the typical choice is this one. So it is a function that is defined on some interval. So you have A, which is the soup of your psi. You don't want the function to be defined here. So here you don't require anything. And you want a function that is concave like this. So it goes from a finite limit that, of course, you can normalize to be 1 if you want. So this will be my function rho, and it goes to some other value, say b here. Okay, and you want it to be concave at least on some interval near minus infinity. So, for instance, this function works. So 1 minus something that, let's say, branch of hyperbola. So it works perfectly well. A technical condition needed. So alpha is the constant that will be related to the curvature. A is the soup of psi. Okay. And you need this technical condition, which is satisfied for this choice, but it's just technical. And now the estimates will involve integrals of the following form. So you correct the exponential minus psi by the absolute value of the derivative rho prime of psi. So for instance, if you take that one, the derivative rho prime of psi is a constant psi minus square. And you see that in the case of log canonical singularities, is just what is needed to make this canonical singularity that would be integrable with 1 minus epsilon here. But actually, if you just divide by psi square, it's enough to make it integrable. So it's just a very small extra factor that makes the weight to be locally summable everywhere, including on the singular set. Okay, so now I can state the theorem. So it was proved a little bit more than one year and a half ago. So it was late 2019. So you take a weakly pseudoconvex Kähler manifold, L a homomorphic line bundle equipped with a singular Hermitian metric H, H0 exponential minus phi, and an additional weight psi locally integrable. Then you assume that there is a constant alpha positive and small, such that the curvature theta LH plus I del del bar psi, or 1 plus alpha I del del bar psi is non-negative. Then, assuming that the total integral of this residual measure here is finite, you can get, and you assume here that, of course, this implies that f lies in the restricted multiple ideal, because by definition you are locally finite since you are globally finite. Then there exists a global extension. I forgot here, I close the parenthesis, with values in this thing, which of course is contained, it's smaller than what you would expect. So you have an extra condition. Okay, the previous qualitative theorem of yesterday was able to extend any section here in I of h, but you lose the L2 estimate, because if you have I of h here, the integral may be infinite. And although it is infinite, the surprising fact is that you are still able to solve, but you lose the L2 estimate. If you want to keep the L2 estimate, you need a stronger condition. So you need a stronger vanishing of f. But when this is true, you get the following explicit L2 bound, that the total integral over x of capital F square with respect to this flexible weight here is less than the constant times the integral over y of your given section small f. And here the constant is just the value of rho at minus infinity. And the constant here is absolutely optimal. So it's 1 here. And this will be important for some applications. For many applications, it's not important. It's enough to have a constant, but it turns out that there was a conjecture that is now solved, the Suita conjecture, which depends on having the optimal constant. So it's important to know the optimal constant. Also, this is related to the Bernson direct image theorems, and for such theorems, you definitely need also the optimal constants. Okay, so now I'm going to briefly sketch the proof. So it's very parallel to what I explained yesterday, but differs in some details. Okay, the difference is first that you don't consider HQ here, but just H0. Okay, so you have a holomorphic section. I will have later to assume that it's in I prime, say, of H. Okay, but of course, at this point, I assume just I of H. And you have a smooth lifting, as I already explained, by taking a Stein covering and a partition of unity. But of course, it's not holomorphic. So you look at del bar, and of course, this local lifting is holomorphic. So you get the sum of del bar Xi times Fi twiddle. But the trick is to subtract some given, the sum is over I here. So if you subtract any one, because the sum of del bar Xi is 0, you still get del bar F twiddle. But now the difference has values in this subsheaf, and therefore you see that the del bar has values in the smaller ideal sheaf, this one, not the big one, okay? And because here you are in the smaller one with safety coefficients anyway, this is going to converge with the additional weight exponential minus psi, at least if you truncate to a relatively compact open subset. But because X is assumed to be weakly pseudoconvex, you can exhaust X by looking at the sublevel sets of your exhaustion functions. So now you are on a compact subset, and because of a local integrability, it will be convergent. So then you will get estimates on XC, and then you will let C go to infinity at the end. So I'm going to be very brief on these details. So next, you truncate. Okay, because here you have a global smooth function, but you somehow control the curvature only close to your subvariety. So you are going to introduce the small hollow tubular neighborhoods that I already defined, and you multiply by a cutoff function, which you take to be theta of psi minus t, so that it exactly has support here in the full tubular neighborhood. So the support of this includes the whole, of course. And now you want to solve the d-bar equation, where d-bar of the solution that you look for is Vt, which is just the del bar of your truncated theta of psi minus t times f twiddle, which is equal to theta psi minus t del bar of f twiddle plus theta prime psi minus t del bar psi wedge f twiddle. And now this one has support here in the green part. So because theta prime is also 0, where theta is 1, and theta here is 1 here in the whole, theta is 0 here, and just varies between 1 and 0 here in the green part. Okay. Of course, the goal is to be able to work even with non-smooth weights. And if psi and phi happen to be not smooth, well, I will skip the details, but essentially you use at this point regularizations. The regularization may still have some singularities, as I will explain later. But then the poles are on some analytic set, and then you can find complete calorimetrics that decay to your calorimetric that are complete on the complement, and then you can easily deal with this non-smoothness, and then you are essentially reduced to a smooth case. Okay, and now you apply the approximate L2 existence theorem that I stated yesterday with some twisting factors. So I don't recall the exact formula. I don't recall exactly myself the all terms now without seeing it. But you get then an approximate solution ut epsilon and an error term, and the sum of the corresponding integrals are bounded by the inverse of the curvature multiplied by the two terms that appear here on the right hand side. Okay, so you have one term here and another term here, which you have to bound. These two terms give these two integrals. So the first integral is very mild because we have seen that this thing is integrable with respect to this weight. And therefore, if the tubular neighborhood shrinks to empty set, well, shrinks to y, this will converge to 0. So no problem with the first term here. The second term is more subtle, and this is exactly where you have to compute a lot. And now the difference with yesterday is that we didn't try to to bound a solution. We only wanted to bound the error. And for the error, we have an extra term epsilon, which helps a lot, because you multiply by epsilon, and then the epsilon multiplied by this is bounded. So you are in good position. But now it's even better, because we are going to show that this one is bounded. And therefore, the error will go to 0, and the solution will be bounded at the same time. So this is the trick. Okay, so the first integral goes to 0. So this is by Fatou. And then you have to choose carefully the twisting factors to make the things, the second integral here to converge. So I will not make the calculation. They are essentially identical to what Ozawa has introduced long ago, and that has been gradually slightly improved. It turns out that to get the optimal weights, the optimal constants, you have to take this. It's completely explicit in terms of rho and the data, but of course the calculation here is not very enlightening, so I will completely skip it. And then you show it works, and you get the estimate. Okay, let me give a rather simple case. So suppose you are on a Stein manifold, and suppose you want to extend from a hypersurface. So you assume that you have a holomorphic function W, which defines essentially your hypersurface, y equal W minus 1 of 0. You assume that you possibly have some singularities, so you look at y0 to be the regular open subset of y. You assume that you have a weight which satisfies this condition, that sup over x of psi plus 2 log W is negative. So you are using actually this as the what I denoted by y before. And then you get the very explicit formula. Suppose you have an n-1 form. So you multiply f by f bar, so you get a volume form up to the constant I to the n-1 square with respect to the weight phi minus psi. Then you extend, so I think I've forgotten here something. So you get an integral of f, which f bar, exactly with a constant which turns out to be equal to 2 pi with these normalizations. The important thing is that you have the best optimal constant 2 pi here. So here, because I pass from an n-1 form to an n form, actually I have to multiply by dw, but it's just a minor change of notation, of course. Dividing by dw would mean that I recover the previous theorem. So it's a very special case of the general statement. And it turns out that it is, in the one variable case, what gives the solution of the so-called Suita conjecture. So the Suita conjecture was posed originally for open Riemann surfaces in 72. And the question was to relate for Riemann surfaces the Bergman kernel with the green function g omega. Of course, you have to assume that that the Riemann surface possesses a green function. Okay. And then you can define the logarithmic capacity at a point z by looking at the behavior of the green function near the diagonal. So you let xi converge to z, so it has a logarithmic pole, and you look at the constant. Take exponential limit of g omega xi z minus log xi minus z in some coordinate, and you get a constant. Of course, it depends on the choice of the local coordinate z. But it turns out that if you multiply by the square of dz, then now this is easily seen to be independent of the choice of the local coordinate. Because essentially, if you choose another one, it will behave locally as multiple, but then the multiple is involved in the logarithm, and then it's killed here in the product. Okay, so this product is independent of the local coordinate. And the Suita conjecture was that what you get here as this volume form is bounded by exactly pi times the Bergman kernel. So now it's a theorem that was proved in the case of plane domains by Brodsky in 2013, and in the general case by Guan and Zhou in 2014. And it's a consequence of the previous theorem in dimension 1. And moreover, Guan and Zhou proved that the equality holds. You can completely characterize if and only if the domain is bilomorphic to a disk minus a closed polar set. Of course, if you remove a polar set, you don't change the Green function. And then, well, it's easily seen that it doesn't interfere with the result. I will not give the details, but will prove something which is very much related. I should also mention that Osawa, Osawa, of course, gave the general lines of the strategy, but he didn't have the optimal constant, so he got something a bit weaker. Osawa also stated a general version in dimension n, and this general version is also okay, except for the equality case. But there is also a corresponding inequality in an arbitrary dimension. And now I will explain something slightly different, which is an old theorem of mine for approximation of currents and Zariski decomposition. It's very much the same idea. So you consider Kähler currents on a compact Kähler manifold. So by definition, a Kähler current is a current that is positive and bounded below by some smooth, strictly positive Hermitian metric multiplied by a small factor, delta. And you can consider the cone of cohomology classes. This is exactly what is called the cone of big classes. Cone that dominates in the sense of pseudo-effectivity Kähler classes. And then the theorem is that any Kähler current can be obtained as a limit of currents which now have analytic singularities and logarithmic poles. And you can find modifications mu m in the sequence, x twiddle m to x, such that the pullback of your current now becomes a normal crossing divisor, you can even assume em, plus a Kähler form beta m on the blow up x twiddle m. So in that sense, you approximate what is a priori a very complicated current by something that by a resolution of singularity becomes relatively simple. It just has divisorial singularities plus a Kähler form. And the coefficients here can be taken to be with denominator m. And moreover, this was observed by Buxom in his PhD thesis in 2002. The volume of that Kähler part here converges to the volume of the class here, the volume of the current as m goes to infinity. Okay, and I have only 1 minute to give the proof. So you write locally, you use the potential of the current, will be strictly pluri-subharmonic. And then you look at the Bergman kernel. So you look at the Hilbert space of functions that are integrable with respect to the weight exponential -2m phi. Look at the Bergman kernel and take 1/2m times log of the Bergman kernel. As is well known, the Bergman kernel is obtained by taking the soup over all functions of norm less than 1 of the log of the values of the function at this point. So you take 1/2m times the soup of the log. And then the mean value inequality, you just restrict to a ball. And then, of course, it controls up to the soup of phi. It controls the usual L2 norm, and by the mean value inequality on a ball of radius r. So it should be zeta here. So f of z square is exactly less than this. And if you take the log and divide by 1/2m, you see that phi m is less than this. Okay, that's somehow the trivial inequality, that's the mean value inequality. On the other hand, you just apply now the pointwise Ozawa-Takeuchi theorem. So even if you extend from one point, it's highly non-trivial. So you take the function to be equal to exponential m phi of z0 multiplied by a small constant. And then you have the global extension in your ball. The global L2 norm is less than the constant that depends only on the diameter of the ball, times the integral on the point, so it's just a direct measure. But you have chosen here this value, and you choose small c equal to capital C minus 1/2. So then this will be 1. So you get a function that has norm less than 1. And by the previous formula, the soup now is larger than phi of z plus 1/2m log z. So you get an inequality that this is less by the mean value inequality. Okay, so it's less than the mean value formula here. And it gives you a very precise estimate of the low numbers. They are actually converging to the low numbers of phi. And then you can get the global approximation by looking at the partition of unity, taking balls, approximating locally, and gluing by the partition of unity. And then, of course, you have a lot of calculation that I will completely skip. And this result turns out to have many, many applications, but definitely there is no known proof without the Ozawa-Takeuchi. And you see that even for one point, it's a highly non-trivial theorem. Okay, I think my time is over already, so I will stop at this point for today.
Thank you very much, Jean-Pierre, for the beautiful talk. Please, are there comments, remarks, or questions? There is a question on the chat.
Okay, so let me look at the chat. Doesn't partition of unity spoil the approximation? That's a good question. Of course, I have skipped the proof. Let me give you the idea. Okay, so you have a covering by balls, say omega 1, omega 2, omega j. On each of the ball, you have a local approximation Pam, which itself is 1/2m times the sum of, log of sum. I have to remove my window. Okay, log of a sum of G, J, M, L square, okay, sum over L. So L is the, say, in natural numbers, so Hilbert basis, okay? So you have this complicated sum. Now you take the phi M to be Z to be 1 over 2m times log, I'm cheating a little bit, but essentially that's the idea. Now I take a partition of unity and now, of course, you have to compute I del bar of phi m. So when you do this, you definitely have derivatives of theta j that come into play, but the partition of unity is fixed and you divide by 1 over m. So the trick is that the derivatives of the theta j are divided by m. So you may hope them to go to 0. Actually, you have to use a square partition of unity. So you assume that your functions are square. It works well. Of course, doesn't change much. And then you have a simple formula, provided you can show that your Bergman kernels are comparable on 2 overlapping balls. So you definitely have to compare what you obtain on 2 overlapping balls. Of course, you shrink a little bit the balls, so you actually compare only on a small compact subset of the intersection of the balls. And here you can use Ormander's L2 estimate to show that the Bergman kernels are comparable. So it's not a non-trivial result, but definitely relies on not very difficult estimates. Of course, you have to use again deep L2 estimates. So that's the main trick.
Okay, more questions? This is not the case, so thanks again, Jean-Pierre, for the beautiful talk. We will resume at